All right, so today we're going to talk about solving systems by graphing. We can use the graphing method of solving systems of equations most easily when we have numbers that are easy to work with and when our equations are in slope-intercept form, just like this system right here. So starting off, we're going to graph both of these lines on the same coordinate plane. So in this equation, my slope is 3, or 3 over 1, and my y-intercept is negative 2. So I'm going to plot my y-intercept, and then go up 3 and right 1, and down 3 and left 1. Next, I'm going to graph the second equation on the same line. So this slope is negative 2 over 1, and this y-intercept is positive 3. So I'm going to start at positive 3 on the graph, and I'm going to count down 2, and this time right 1, to make my line, my slope negative. Down 2, right 1, down 2, right 1, or up 2 and left 1. After I do that, I can find the solution by looking where these two lines intersect. So the question asks, what point is a solution for both lines? Well, this point right here is a solution for both lines. And that point's 1, 1. And I can check and make sure that this is true by plugging in that point into my two original equations. So y equals 3x minus 2 and y equals negative 2x plus 3 are my original equations. If I plug in 1 and 1 for both x and y in both of these equations, this resulting statement should be true. So, for example, 1 equals 3 times 1 minus 2, and 1 equals negative 2 times 1 plus 3. So 3 times 1 is 3, minus 2 is 1, so that's true. And negative 2 times 1 is negative 2 plus 3 is 1, so that's also true. So both of these prove that this point is a solution for both of these lines. Right here is just a quick reminder of what a system of equations is. We should have this information in our vocabulary page. It's a set of equations. That's what this little bracket right here means, the set of. It's a set of equations that have the same variables. Okay, and our solution is always an ordered pair. An ordered pair always looks like this, x comma y. So you're always going to have two numbers in your solution, an x value and a y value when you're solving a system. All right, moving down to our first example. This is the steps for graphing a system of equations, which we just followed, and we're going to do one more time above, or do one more time the same as we did above. So my slope in the first equation is negative 1. My y-intercept is 4. My slope in the second equation is 3, because that's the coefficient of x. My y-intercept is 0. There's no constant added to the term with x here. So that means it's going to pass through the origin. Okay, so I graph each equation. My second step is to find the point of intersection, which in this case is 1, 3. And then my final step is that I can check using substitution like I did up here to determine if it is a solution to both equations. So my y value in this case is 3. My x value is 1. I have to make sure I drop down that negative sign in my equation for this first one. And this is a true statement. Negative 1 plus 4 is 3. And 3 times 1 is also 3. So that proves that it's true. You don't always have to do this step, but it's a good step to know how to do to make sure that I do in fact have the right solution to the problem. But this is my actual answer to the problem. Just like up here, this is my actual answer to the problem. Okay, let's open it up and do some more. So the difference in this system is that these equations are both not in slope-intercept form. The first one is in standard form, which is okay. We can still solve it using the graphing method. We would just either graph that first equation using the x and y intercepts, or we can convert it pretty easily to slope-intercept form, which is how I'll do it. So it's currently in standard form. Let's make a note of that. And I'm going to convert it to slope-intercept form. So to do that, I need to isolate y. I'm going to subtract x on each side, and I'm left with y equals 2 minus x, or I can rewrite this as negative x plus 2. And now it's in slope-intercept form. So my slope would be negative 1 over 1, and my y-intercept would be 2. So I'm going to start at 2 and go down 1 and right 1, or up 1 and left 1. The second line's already in slope-intercept form, so I'm just going to identify the slope, which is negative 4, and the y-intercept, which is negative 1. I'm going to start at negative 1. And I'm going to go up 4, 1, 2, 3, 4, and left 1, or down 4 and right 1. But if I go that way, I have to make sure I extend up this way as well so I can actually see where it crosses the other line, which is right here, which is my answer or my solution, the point negative 1 comma 3. And I'm going to skip the checking step on this one. Move on to the next. Our last example, both of these equations are in standard form. So I'm going to go ahead and use the intercepts method of graphing these. So to do that, I'm going to write the first equation, 2x plus y equals 5. And I'm going to see what the y and x intercepts are by plugging in 0 for x and then 0 for y and seeing what the corresponding values are. So if I plug 0 in for x, obviously y equals 5 because anything times 0 is 0. So my first point, or my x-intercept, my y-intercept would be 0, comma 5. And then I can do that again. By plugging 0 in for y. And now I would need to divide by the coefficient 2 to isolate x. And I see that x equals 2.5. So now I write that point as an x-intercept 2.5, comma 0. Okay, so once I have that, I can graph those two intercepts, so 0, comma 5, and 2.5, comma 0. And then I'm going to do that again with my other line. So my next equation is negative 3x plus y equals 0. If I plug in 0 for x, I see that y is also 0. So this line is going to go through the origin. And then if I do that again and plug in 0 for y, I'm also going to see that this intercept is 0, comma 0, which makes sense because your line is going to pass through the origin, right? So you're not going to have a different y-intercept and x-intercept because it's crossing on 0, 0 for both axes. So honestly, this method isn't helpful in this scenario for graphing this line. So I'm going to have to instead convert this to slope-intercept form to figure out how it's graphed. So I'm going to go over here and I'm going to write slope-intercept form method. And I'm going to convert this second equation to slope-intercept form. So I have negative 3x plus y equals 0. And to get it in slope-intercept form, I'm going to get y by itself, and I'm going to do that by adding 3x to both sides. And then y is going to equal 3x plus 0, or just 3x. So my slope in this equation is 3. My y-intercept, as I already know, is 0, right? And I'm going to start now at 0 and use the slope 3 over 1 to help me graph. So up 3 over 1, up 3 over 1, or down 3, left 1. And now I can identify my solution finally, which looks like 1, comma 3. So in that problem, graphing using the intercepts method wasn't so great. If I were to do it again, I'd probably just convert both to slope-intercept form right off the bat, and see that on this one, when I subtract 2x to the other side, I have a y-intercept of 5, and then I go down to left 1. But just so that you know, both are available to you. Our last problem is a real-world problem. It says, during school vacation, Mark wants to go bowling and play laser tag. He wants to play 6 total games, but needs to figure out how many of each he can play if he spends exactly $20. Each game of bowling is $2, and each game of laser tag is $4. So bowling is 2, and laser tag is 4. Let X represent the number of games Mark bowls. Okay, so bowling is X. And let Y represent the number of games of laser tag Mark plays. So laser tag is Y. and write a system of equations that represents the situation, and then write the equations in slope-intercept form. So this is kind of giving us a hint as to what to do already. It says write the system, then convert the equations to slope-intercept form. So this is kind of a hint that we're going to write our original equations in standard form. We have two different types of equations we're going to set up here. We're going to set up an equation that represents the total amount of games, and we're going to set up an equation that represents the total amount of money. Remember to use this bracket. That means the set of. And then we're going to write our two equations. So he bowls a certain amount of games, and he plays a certain amount of laser tag games, and he plays 6 games total. So my total amount of games is going to equal 6. He also spends a total amount of money of $20. So my total amount of money is going to be 20 in my other equation. And now I just need to figure out what I'm adding on this side. So I always find the one that has to do with money to be easier. So each game of bowling is $2, and X is my amount of bowling games. So 2 times X plus laser tag is $4, and laser tag is Y. So 4 times Y. And that's going to equal $20 total. I always find that one to be easier to set up. The total amount of games is also really basic. We just know that the amount of bowling games is X and the amount of laser tag games is Y. So this first equation should just say X plus Y equals 6. And then we have our system. So now I'm going to write those equations in slope-intercept form. So I'll start with X plus Y equals 6. To convert that to slope-intercept form, I'm going to isolate Y by subtracting X from both sides. So Y equals either 6 minus X or negative X plus 6. Okay, and then I'm going to do that again with 2x plus 4y equals 20. So 2x plus 4y equals 20. Remember, the goal is to isolate y, so I'm going to start by canceling out the term with x. And now I have 4y equals 20 minus 2x, or negative 2x plus 20. And then I do need to do one more step on this one to isolate y. I need to get rid of that coefficient of 4 by dividing both sides by 4. Remember to divide the entire expression by 4. So you're dividing both negative 2x and positive 20 by 4. So this is going to say y equals negative 2 divided by 4 is the same thing as negative 1/2 x, or negative x over 2, however you want to write that. And 20 divided by 4 is positive 5. Okay, so now in my system, I have this equation and this equation. And I can graph these lines next. So they have a graph set up for me here. I do need to label this graph. So remember why they wanted us to make laser tag. So I'm going to label this laser tag. And X bowling. And now I'm going to graph y equals negative x plus 6 first. My slope in this line is negative 1 over 1. and my y-intercept is 6. So start at 6, go down 1, right 1. And next I'll graph this one, which my slope is negative 1 over 2, and my y-intercept is 5. Start at 5 and go down 1 over 2. And the point of intersection represents the number of games of bowling and the number of games of laser tag Mark can play. So that point is 2, 4. And in real-world problems like this, we want to make sure that we say what this solution means in the context of the problem. So if Mark spends exactly $20, he can play 2 games of bowling and 4 games of laser tag. One more quick note I want us to make on this note taker in our margin over here is special types of solutions with systems. So all of the solutions that we've seen so far have intersected at one point. And when that happens, there is just one solution to the system. But there is going to be situations where your lines never intersect. Those lines are called parallel lines. And if your 2 lines never intersect, that means that there is no solutions to the system. And then one more special type of solutions would look like this. You would graph a line, and then you'd be given a second equation, but it would end up being the same exact line that you graph directly on top of that other line. It's going to appear like one line on the page, but there's actually 2 equations. If that happens, that means that both of these lines intersect each other at every single possible point, and we call this infinite solutions.